In this video, we look at the energy levels of a hydrogen atom and the possible transitions between them. For a hydrogen atom, the bound stationary states are characterized by three quantum numbers. N equals 1, 2, 3, and so on, is called the principal quantum number. L, which can be 0, 1, and so on, all the way up to n minus 1, is called the angular momentum quantum number. And finally, M equals 0, plus minus 1, and so on, all the way up and down to plus minus L, is called the magnetic quantum number. States with different values of L are labeled with letters. States with L equals 0 are called S states. L equals 1, P states. L equals 2, D states. L equals 3, F states. And so on. The energies of the bound stationary states are given by En equals negative a quarter times 2me over h bar squared times ze squared over 4 pi epsilon 0 squared times 1 over n squared, which, when evaluated numerically, gives negative 13.6 electron volts times z squared over n squared. Z is the nuclear charge and equals to 1 for the hydrogen atom. Although there are three quantum numbers, the energy depends only on one, on n. Therefore, states with identical n but different L and M have the same energy. They're degenerate. For each energy, En, there are n squared degenerate states. Let's plot the energy levels for hydrogen. Let's plot the energy in units of electron volts. Here is 0. For the lowest energy state, we get minus 13.6 electron volts. That is for n equals 1. For n equals 2, we get negative 3.4 electron volts. For n equals 3, it's negative 1.5 electron volts. And so on, with ever decreasing spacings. N equals 4, and so on, all the way up to n equals infinity. The energies of all the bound states are negative. Each level represents a total of n squared states that are all degenerate. The spacing between adjacent levels decreases with increasing n, and as n approaches infinity, the energy converges towards 0. This zero energy corresponds to a situation where the electron and the nucleus are infinitely far apart and at rest. Transitions between excited states down to the ground state are the following: 2 to 1, 3 to 1, 4 to 1, and so on. They're all allowed. This series of emission lines is called the Lyman series and occurs in the UV. Also, a hydrogen atom in the ground state can absorb these photons and go from the ground state to the corresponding excited state. Emissive transitions from higher excited states down to n equals 2, 3 to 2, 4 to 2, 5 to 2, and so on, form the Balmer series, which of course occurs in a visible. Transitions down to n equals 3 form the Paschen series and occur in the IR. Let's start assembling the selection rule for these electronic transitions. Obviously, we have allowed transitions independent of the values n of the initial and the final state. So, the change in n, delta n, is unconstrained. We can go from any energy level to any other. Let's plot the energy levels in more detail, separating states according to their value of L. For L equals 0, we get states for n equals 1, for n equals 2, for n equals 3, 4, and so on, all the way up to energy of 0. Each of these levels represents only one state: the 1s state, the 2s state, the 3s state, and so on. For L equals 1, we get states only for n equals 2, 3, 4, 5, and so on. Each of these levels represents 3 states: the 2p states, the 3p states, the 4p states, and so on. For L equals 2, we have groups of 5 states that start at n equals 3, n equals 4, 5, 6, and so on. These are the 3d states, the 4d states, and so on. This continues for higher L. Now, transitions between states are allowed only under 2 additional requirements that add to the selection rule. First, the angular momentum quantum number changes by exactly 1. So delta L has to be equal to plus or minus 1. Second, the magnetic quantum number, m, is allowed to change by maximally 1. So it's either 0 or plus or negative 1. So transitions to the 1s ground state are possible only from the 2p excited states or from the 3p excited states, but they're forbidden from the 2s excited states. Similarly, to get to the 2p states, we can get there from the 3s states or from the 3d states, but not from the 3p states. These transitions are forbidden. In summary, we have seen that there is a high level of degeneracy in a hydrogen atom. There are 3 quantum numbers: n, L, and m. But the energy only depends on one quantum number, on n. These energies are all negative. We also saw the selection rule for electronic transitions in a hydrogen atom. Transitions are allowed for any combinations of n, but changes in L are limited to plus minus 1, and m can change by 0 or plus minus 1 only.